Hello, welcome. This is Physics 104B, the Chapter 22 homework. And the picture you see on the screen is from the PHYS simulation. We have a bunch of charges, some positive, some negative. The white arrows represent electric fields, and the green curves represent the equipotential lines. And a lot of that was some of the topics in this chapter. Let's start with number 17. It takes 45 joules to move a 15 millicoulomb charge from point A to point B. What is the potential difference delta VAB? So the potential difference between points A and B is given by this equation. It's the difference in potential energy over charge, which is the work that it does divided by the charge. And so we do 45 joules divided by 15 times 10 to the negative 3 coulombs, and we get a potential difference of 3,000 volts. Number 19, find the magnitude of the potential difference between 2 points located 1.4 meters apart in a uniform 650 Newton per coulomb electric field if a line between the points is parallel to the field. And so I've drawn a simple picture there between A and B. And we're going to just look at the magnitudes between these. So that's why I've used the absolute value signs, using the equation, but just concerned with the magnitudes because we're not actually sure what direction it should be going. But we can say it's 650 volts per meter times the difference or the distance 1.4 meters, and we get 910 volts. Number 21, a proton, an alpha particle, which is a bare helium nucleus, and a singly ionized helium atom are accelerated through a 100-volt potential difference. How much energy does each gain? So we'll think about these three different charges. A proton has a charge of plus E because it's just a single proton. The alpha particle, a helium nucleus, has two protons in it, so plus 2E. And the third particle, a singly ionized helium atom, has two protons and one electron, so the net charge is plus E, the same as the proton. And so for each of these, the question is asking how much energy does each gain? So we'll say that the change in potential energy is the charge times the voltage difference that it goes through. So for the proton, charge times 100 volts, and we get 100 electron volts. For the alpha particle, 2E times 100 volts is 200 eV, or electron volts. And for the helium ion, it's 1E times 100 volts, and that's 100 electron volts. Now I've converted all those to joules, and so you can see those energies in joules. Number 23. An electric field is given by, and you can see up at the top, E naught J hat, where E naught is a constant. Find the potential as a function of position, taking V equals 0 at Y equals 0. So let's draw a picture here. If E is E naught J hat, then it's a uniform electric field going in the positive J direction. And it's also telling us that at Y equals 0, V equals 0. So there's the setup. And we want to know the potential V as a function of position. Well, here's the equation that relates potential to electric field. We have this integral here. And since it's all constant, it's a uniform field, we actually don't need the integration. It's just going to be negative of the dot product between the E vector and displacement. And then we look at the left-hand side of the equation, the potential difference between A and B. Well, let's take the difference between a given position, Y, and Y equals 0. So that becomes V at Y minus V at 0, which I've crossed out because it's equal to 0, equals the right-hand side. I've left that the same. And then we can say that the V, the electric potential at Y, is equal to, and we have the dot product, and here I've gotten into what is that dot product. Well, breaking it down, the E vector is negative E naught times J hat, which I've shown at the top there. And then the dot product displacement is going to be however far it's gone up in the Y direction, so Y times J hat. So when we do the dot product of these two vectors, it's going to be the magnitudes multiplied times the cosine of the angle between them, but they're both going in the same direction. So that's times the cosine of 0 degrees, which is 1, and we're left with negative E naught Y. Number 25. The potential at the surface of a 10 centimeter radius sphere is 4.8 kilovolts. What is the sphere's total charge, assuming charge is distributed in a spherically symmetric way? You can read about a sphere. It's a bit more complicated than an example, slightly, in example 22.3 in the book. But it says that the field outside such a distribution is identical to that of a point charge. And so we're going to treat it like a point charge, as long as we're talking about outside the sphere. And so on the surface is considered outside of the sphere. So the potential at some place R, some distance R, is kq over r, and we're going to take r to be the radius of the sphere. So all I've done in this top line is turned the variable r into the radius, capital R, of the sphere. And so then we're going to solve that for Q. Q is the radius of the sphere times the voltage at that position, 4,800 volts, divided by K. And you can see here in the denominator in class and in my lecture videos, I might take that out a few more digits, 8.9876 times 10 to the 9th. But here, just to, I guess, save a little time in writing, I just used 9 times 10 to the 9th. You should use the more fuller, more precise version, 8.9876. But we get 5.3 times 10 to the negative 8 coulombs. Number 27. A 3.5 centimeter diameter isolated metal sphere carries 0.86 microcoulombs. Find the potential at the sphere's surface. And if a proton were released from rest at the surface, what would be its speed far from the sphere? All right, so we're going to do part A just like the previous problem, number 25, where the potential at the surface, it's as if that 0.86 microcoulombs were a point charge that distance away. So we do K times the charge over the distance, which is the radius of the sphere, and we get 442,000 volts, or 442 kilovolts. Now we're going to look at part B. If the proton were released from rest at the sphere, so you can imagine the sphere has a positive charge, a proton is positive, so it's going to instantly spring away. It's going to be pushed away. And it's saying at a very far distance. It says, what will its speed be far from the sphere? So we can take that as an infinite distance, but let's look at this, see what we do here. We're going to look at the change in potential energy as it goes from A to B is equal to the charge of the proton times the potential difference. And let's plug these in. The charge is E. The potential difference, a far distance away. I'm sorry, let me back out of that sentence and start again. The potential, a far distance away at position B is 0. You get far enough away and it's just 0. And we're left with just negative V sub A. So we have negative E times the potential difference at A. And we already know the potential difference at A. We got that up in part A, 442,000 volts. So negative E times that is negative 442,000 electron volts. Let's convert that to joules, and we get negative 7.09 times 10 to the negative 14 joules. Now, what we've figured out so far is the change in potential energy. Let's now relate that to change in kinetic energy. So we're using conservation of energy here. The change in kinetic energy is the opposite of the change in potential energy. So if it lost 7.09 times 10 to the negative 14 joules of potential energy, it gained that much in kinetic energy. It started at rest, so we can say the change in kinetic energy is 1/2 mv squared. And then we're going to solve for v. You can see the algebra I've gone through. V squared is 2 times the change in kinetic energy over mass. In the denominator is the mass of a proton. Plug those in, we get 9.2 times 10 to the 6th meters per second. Number 31 says the electric potential in a region is, you can see that at the top, with V in volts and coordinates in meters. Find the potential and the components of the electric field at a point x equals 1 meters, y equals 1 meter, z equals 1 meter. All right, so first of all, the potential. This is just plugging in the values for x, y, and z. So we get 2 times 1 times 1, which is 2, minus 3 times 1 times 1, so 3, plus 5 times 1 squared plus 5, and we add them together, 2 minus 3 plus 5, and we get 4 volts. Now for the second part, we're looking for the electric field, and this equation uses partial differentiation. The electric field as a vector is the opposite of, and its x component is the derivative of potential with respect to x. The y component is derivative with respect to y, and the z component is derivative with respect to z. So when we do this partial differentiation, we are only, for example, for the first one, for the derivative of v with respect to x, we are treating y and z as constants. We're only treating x as the variable to take the derivative with respect to. So this first term, again, thinking of y as a constant, is 2y minus 3z, and then there's nothing with regard to x in this third term, so that's just plus 0. So the first term is 2y minus 3z. The second term, when we take everything with respect to y, the first term is 2x, the second term is 0, and the third term is 10y, so we have 2x plus 10y. And then finally, we take the derivative of potential with respect to z, and the first term is 0, minus 3x, and the third term is 0, so we have minus 3x. And then we are to find, as the question says, find the components of the electric field specifically at x equals 1, y equals 1, z equals 1. So we're going to plug in those values. 2 minus 3 becomes negative 1. 2 plus 10 gives us 12. Negative 3 times 1 is negative 3. And don't forget, because very often this is where students mess up, forgetting that little negative sign out to the left. And so it's the opposite of all those. So the electric field at that position is 1, negative 12, and 3 volts per meter in the x, y, and z directions. Number 41. A 5-gram object carries 3.8 microcoulombs. It acquires speed v when accelerated from rest through a potential difference v. If a 2-gram object acquires twice the speed under the same conditions, what is its charge? Okay, so fun little puzzle here. We're not given a lot of information. We're not given the lowercase v speed, uppercase v potential difference. And by the way, this problem is a good example of let's be clear with our handwriting and keep a difference between our lowercase v and our uppercase v. I've written out the given information, so you can see what I've done here. Mass 1, Q1, and V1, I'm just going to call it V. Well, that's what the book called it. So that's V1, the speed of object 1. Object 2, we have M2, Q2, we do not know. In fact, that's what we're trying to figure out. And it says it acquires twice the speed. So V2 is 2 times V. All right. Now let's look at this basic relationship statement of conservation of energy, that the change in kinetic energy is, now it's actually the opposite of the change in potential energy, but I'm more concerned with magnitudes here. Leaving the negative sign would help to discern direction, but I'm really not caring about that, just the magnitudes. So I find it more convenient just to take the absolute value of the magnitude here, and that equals QV in the magnitude, Q times potential difference. So 1/2 mv squared equals Q times voltage. And I'm going to divide both sides by Q and multiply both sides by 2. Now the reason I've done that is this is a technique that we've seen before, where if we have a situation where there's some components in the equation that are equal but some that are changing, I put everything that's changing to the left, everything that's not changing to the right. And so the 2 and the voltage, those are what are constant. The stuff on the left, mv squared over q, that's what's different. And so recognizing that mass times speed squared over charge remains constant, I'm going to set up this ratio. m1 v1 squared over q1 equals m2 v2 squared over q2. And using this technique is great because now we don't care about a lot of the information that wasn't given, meaning we were never actually given what the velocity is. We were never given what the potential is, but that's okay. We don't need those. I'm solving for what it asked me to solve for, so Q2. So we set up these ratios that Q2 is equal to Q1 times the ratio of those masses. Just make sure you do the algebra properly and get them in the right order. M2 over M1 times V2 over V1 squared. And then we just plug everything in. So 3.8 microcoulombs times 2 grams over 5 grams times 2V over V. The V, that speed, cancels. All that we're concerned with is that in the parentheses is that factor of 2 squared, and we get a charge of 6.1 microcoulombs. Problem number 47. Find the potential as a function of position in the electric field AX I hat, where A is a constant and V equals 0 at X equals 0. All right, so going from electric field vector to the potential as a function of position, we start by writing out the electric field vector. Let's set up the equation for potential difference. So delta VAB is the negative of the integral dot product of the electric field vector and dr. And we'll plug in our limits of integration going from 0 to x, because we want to know the potential difference between x equals 0 and x equals x. The electric field vector is AX I hat. dr, and we're really only considering the one-dimensional situation. It's moving in the x direction. So dr becomes dx times the unit vector I hat. And now it makes it easier when I put in I hat notation to do this dot product here. The left side of the equation, recognizing that we're looking at a potential difference between those limits of integration were 0 and x, so it's Vx minus V0. And it was defined in the problem that V of 0 is 0, so let's just get rid of that. On the right-hand side, that dot product becomes AX times dx times the cosine of the angle between those two vectors, but they're both in the same direction, so that's a cosine of 0 degrees equals 1. So inside the integral, we get AX dx. Then we do the integral, a being a constant, and we've got negative a over 2 x squared taken from 0 to x. So the potential at position x is negative 1/2 ax squared. Number 51. A charge plus q lies at the origin and negative 3q at x equals a. Find 2 points on the x-axis where v is equal to 0. All right, so fun little puzzle here. The total potential is we're going to use the superposition principle. It's going to be the potential from the first charge plus the potential from the second charge. And we're looking at some position. So we have to think about how do we put that position down in the denominator. So it's the sum of every kq over distance. Well, let's say that it's at some position x. And I'm just going to put my pointer right there. That is at some position x. It's somewhere between 0 and a. Now, it doesn't have to be there. It could be on this side, or it could be on this side. But let me just put it here for now. And so the first one is k times the charge plus q divided by x, which is the position where the position we're trying to find. And make sure that that makes sense. We're looking at the distance from that charge on the left. It is x. Now, why did I say the absolute value of x? Well, let's say that I have it here at 1. So just x equals 1 right here. So it is 1 away from that left charge, but it could also be here at negative 1. Well, it's still 1 away. So whether it's at 1 or negative 1, it's going to be the absolute value of whatever its x-coordinate is. Now let's talk about the potential from the second charge. And so we're going to do k times that charge negative 3q. And the distance that it is the absolute value of x minus a. So again, that denominator is the distance it is. And it'd be good, play with some different positions and convince yourself that that distance is absolute value of x minus a. Again, let's say that it's at a position of 1. Then that would be the absolute value of 1 minus a. Now, if it's less than that, so 1 is less than a, clearly in my example, then you're going to get a negative number, but we want to turn it positive. And so absolute value of x minus a. What if it were over here? Let's say it's more than a. Let's say it's, I don't know, let's just say 5. Its distance is going to be 5 minus a. So you can see in whatever region you put it, there are 3 regions here. Wherever you put it, the distance from position a is going to be absolute value of x minus a. Now that we have our equation set up, we're looking for any positions x where v is equal to 0. So the first potential plus the second potential equals 0. Let's clean this up, simplify it. We can divide both sides of the equation by k and by q. And notice one thing I've done. So I wrote right there in black, divide by kq. I've moved the second term to the right-hand side of the equation. I subtracted it. So if you're wondering, where did the negative 3 go? Well, I subtracted it from both sides of the equation. So there it's a positive 3 on the right-hand side. So after I've cleaned it up, I have 1 over absolute value of x equals 3 over absolute value of x minus a. Now it's an algebra problem. And we have to be very careful with those absolute values. So if I get rid of the fraction aspects of this, do one line of algebra, and you get 3 times absolute value of x equals absolute value of x minus a. And if those absolute values weren't there, this would be tremendously easier, but we have to think about how to deal with absolute values. So 2 ways to handle this. One solution is, let's think about the different regions. So you see these 3 lines here. Assume this, assume that, assume that. These are, assume that x is in the different regions. So let's assume that x is over here at x is less than 0. Then in that case, we have 3 times the opposite of x. Now, why do I say the opposite of x? Let's say that x is negative 5. Well, the equation we're using says it should be 5. We're taking the absolute value. So if x is negative, it's going to be 3 times the opposite of x equals the opposite of x minus a. And go through, plug in real numbers if you want to, but convince yourself that that's how you would deal with the absolute value if it were on that left region. Once we get that, we have negative 3x equals negative x plus a. I've just distributed the negative signs, and we get x equals negative 1/2 a, which if there's 0 and that's a, would be right about right here. All right, now assume it's somewhere between 0 and a. Well, the equation at the top of the screen, so now it's positive. So 3 times the absolute value of x is 3 times x, because x is positive, equals, and the absolute value of x minus a is a minus x. Again, that works because it is something that is less than a. It's in here. So the absolute value of x minus a is going to be a minus x. Again, think through different numbers, the geometry there, and convince yourself that that's true. Then we run through that and we get 4x equals a, so x equals 1/4 a. So right about where my pointer is, right there. And then the third region that we can try, assume that x is greater than a, so somewhere here to the right. Well, this equation, if x is greater than a, then 3 times the absolute value of x is 3x, equals absolute value of x minus a is x minus a. And when we go through this, we get x equals negative 1/2 a, which puts it right about here. Now that is not a solution given the assumption that we made. I know it's the solution that we got for the first assumption right here, but for the second assumption, it's not a valid solution because the assumption, the numbers we plugged into the equation or the values we plugged in assumed that x was greater than a. So this does not work as a solution. However, we do have these other two solutions right here, negative 1/2 a or 1/4 a. Now I said there are two ways to handle this equation. This way is more straightforward. You probably prefer this way. 3 times absolute value of x equals absolute value of x minus a. Let's just take that equation and square everything. And that will get rid of absolute values right away. So we have 9x squared equals x squared minus 2ax plus a squared. Much easier than on the previous page. We get this in standard form. 8x squared plus 2ax minus a squared equals 0. We have to factor it, and it does in fact factor to 4x minus a times 2x plus a equals 0. And that factors nicely to x equals 1/4 a and negative 1/2 a. Number 57. The annulus shown in the figure carries a uniform surface charge density sigma. Find an expression for the potential at an arbitrary point P on its axis. All right, two ways to do this. There's a calculus way and a non-calculus way. I haven't written out the calculus way. I've done it the non-calculus way. But let me briefly describe the calculus way, and I think it would be a good exercise if you want some practice with it. So in the book, there is example 22.7, potential of a continuous distribution, a charged disk. And you can read through that derivation, and you can see that it takes the charge and it integrates many, many rings from radius 0 out to the full radius. And then the limits of integration for a full disk are radius of 0 all the way out to the radius it uses a. And so you can go through the derivation that they do in that example, but let the limits of integration be the radius of the whole, so from A to B. And you should get, you should derive the answer that I got. Now, I've chosen a different way. I've taken the result that they get in example 22.7, and I think of it like this. It is, imagine the complete disk, and you're going to get some charge covering it. You're going to get some potential from that. And then imagine cutting out the center, removing that disk. So we're going to get the potential from the big disk minus the potential from the little disk. So that's the approach that I took. I'm taking the big radius to be B, the radius of the hole to be A, because that's how it's drawn in the picture in the book. I'm going to remember, I'm going to need this on the next page, that surface charge density is charge divided by area. And so I'm going to need that. I'm going to need that because the question is asking it in terms of surface charge density. And we want to know, what is the potential some distance x? So I start with the result that was given in example 22.7. There it is. Now we have to be careful with the variables that we use. In that particular example, they used the radius of the disk to be A. I'm going to switch that, again, as I wrote at the top. The radius of my hole is A, the radius of my disk is B. So consider the annulus as a large disk with a smaller disk that has been removed. So we have the voltage is the voltage or the electric potential from the large disk minus the electric potential from the small disk. And so I've taken this expression in the middle of the page and I've done it for the large disk of radius B and the small disk of radius A. And now what I want to do is just clean that up a bit. So here we go. Here was the result I got on the previous page. I'm going to substitute in that sigma is Q over A. Now these are circles, so Q over pi r squared. And I want to solve that for charge Q because I want to substitute that in and get rid of Q. So Q equals sigma pi r squared. And now when I see Q, I'm going to substitute that in. Sigma pi b squared for the big disk. Sigma pi a squared for the small disk that has been removed. The b squared and the a squared, you can see those divide out. And when I clean it up, it becomes 2k sigma pi. And we've got these four terms, but notice there's a minus absolute value of x, minus absolute value of x. So those are going to go away. And in the end, we're left with this, that the voltage or the electric potential is 2k times sigma times pi times square root of x squared plus b squared minus square root of x squared plus a squared. And that is the answer given in the back of the book. Problem number 58. The potential in a region is V equals AXY, where A is a constant. Determine the electric field in the region and sketch some equipotentials and field lines. All right, so V equals AXY. Now, if you think about that, what that's going to look like, I've gone down here and drawn that V equals AXY. That is inverse relationship between them. So if we think about X going to the right and Y going up, it's these hyperbolas right here. So these solid curves that I've drawn are the different potentials. High potential up there, low potential down there. And so those are our equipotentials. Now, the electric field. Electric field is the negative of, and it's a vector, so we're going to have these three components. And so we do the partial differentiation with respect to x, with respect to y, with respect to z. And so with respect to x, this is ay. So that's the x component. With respect to y, it's ax. And with respect to z, it's 0. And remember to take the negative sign there so we get the electric field vector is negative ay I hat minus ax j hat. And it might be a little hard to visualize what does that look like, but some things to guide you. Remember that electric field and equipotentials are always going to be perpendicular to each other. And so I've started by just drawing a bunch of curves that are, these dotted lines are my electric field lines that are perpendicular to the equipotentials. And then the only thing I'm missing is, do they go to the left or do they go to the right? And so just play with it, just actually make up numbers and plug them in and convince yourself that, yes, I've drawn them going in the right direction. Number 61. The electric potential in a region is V equals negative V naught times R over big R, where V naught and R are constants and R is the radial distance from the origin. Find expressions for the magnitude and direction of the electric field in this region. All right, so I've written out the given information, and we think if V is equal to a bunch of constants times the distance, then it's going to be spherically symmetric. V is going to change as distance increases, and so your equipotential lines are going to look like these circles. And it reminds us of a point charge, so the electric field lines, remember, which are always perpendicular to equipotential lines, is going to go radially outward. Now, is it inward or outward? Well, remember that electric field lines always go in the direction of decreasing potential. And so if it's negative, potential is negative, and it increases with R, then decreasing is going to be outward. So the electric field lines go in that direction. And now to find the electric field, remember it's the negative of, and the x, y, z components are going to be the partial differentiation with respect to those variables. Let's go to the next page. So there's the equation we're working with. Now, two ways of doing this. One way is to use Cartesian coordinates. There's a smoother way when you have something that is spherical in nature. It's actually more convenient to use spherical coordinates. However, that will depend on your experience and comfort with spherical coordinates. And so I'm showing you the solution with Cartesian coordinates. So we have our E that we're using, and remember V is negative V naught over big R times R. Switching this to Cartesian coordinates, we're going to use Pythagorean theorem that R is x squared plus y squared plus z squared and the square root of that. And so if you look on my second line here, we have the negative, and then we're going to take the x derivative of negative v naught over r times little r, and the y derivative and the z derivative. All right, so when we clean that up, we can, in all of these cases, factor out the negative v naught over r. So I've factored out negative v naught over r. Remember, there already was a negative sign, so those will annihilate each other. So we've got on the outside of our vector v naught over big R. On the inside of the vector, the only thing that was left was, in each of the three cases, deriving r with respect to x, with respect to y, and with respect to z. Now we have to substitute for r. What is it? So the derivative of r, and when you see r, look at where my pointer is. We're taking the derivative of this with respect to x. And so it's going to be 1/2 times x squared plus y squared plus z squared to the negative 1/2 power times the derivative with respect to x of what's in the parentheses, which is 2x. So everything I just said is right down here. Now, for the y component, we're going to take the derivative with respect to y. So the derivative of r, I'm looking up here where it's written out, derivative of this with respect to y is 1/2 x squared plus y squared plus z squared to the negative 1/2 power times the derivative with respect to y of what's in the parentheses, so 2y. And then I repeat that again for the z derivative. It's going to be the same thing in 2z. Now, cleaning that up a bit, x in every one of these terms is x squared plus y squared plus z squared to the negative 1/2 power. And that means 1 over the square root of x squared plus y squared plus z squared. Well, that's just 1 over r. And so we also clean up, there's a 2 and a divided by 2 and x. So in the end, it all cleans up to be x over r, y over r, z over r. Well, let's factor out that 1 over r, put it there, and we get v naught over big R little r and the vector x, y, z. Now the vector x, y, z is the position vector. It's the r vector. So I've replaced it there. So that cleaned up very nicely. That's the vector of the electric field, just v naught over big R times r hat. Now r hat is just the radial, the unit vector going out. So we could say that the magnitude is v naught over r, and the direction is radially outward. We could also do this using spherical coordinates. So if you like using spherical coordinates, you can follow along with this. It's actually a lot cleaner. But if you're not comfortable with spherical coordinates, that's okay. You can just skip this part right here. What we have to do first is convert all of these x, y, and z components to spherical coordinates. And so here I've converted it to the r hat vector, to the phi hat vector, and the theta hat vector. And so when we do each of those three derivatives, we do the derivative of voltage with respect to r in the r hat direction. It doesn't depend on phi or theta, and so those derivatives just go to 0. Well, that cleaned it up nicely. And so then we have negative of derivative of electric potential with respect to r hat, and we go back to the equation given for V, and so we can see the derivative of that is negative V naught over R, and we're taking the negative of that, and so we get V naught over R times R hat. So again, as we found with the Cartesian coordinate solution, that would be a magnitude of V naught over R times R hat. That is the end of the chapter 22 homework. Have a great day.